optimize. And we can not use, for example, only stirred reactor. It's difficult to remove the sludge. That's why we have to design a reactor that's possible to have without mechanical power. So to optimize, we have to optimize the energy, the mechanical energy, the electrical energy, etc., etc. So we talk about airlift concept. What is airlift? It's a particular class of bubble column. We have two compartments. One compartment with the gas and liquid, and one other without gas. So we have difference of density or pressure. So we have induced flow of liquid because of difference of density between compartments. This is the concept. Okay, we use this concept to design a special reactor to have this electrocoagulation. Okay, this is the concept. You can deduce the velocity of the liquid in the reactor. Yes. Yeah. So the goal, our goal is to optimize the wastewater treatment by electrocoagulation, concerning the cost and the energy, etc. So innovative treatment by combining electrocoagulation with an external loop reactor is interesting. We will combine the concept of a reactor with the electrocoagulation to have a good process, for minimum consumption of energy and so on. Yes. So what we can another next. The concept is no one. We can yes we can yes. Okay. So what is external airlift reactor? As I said we have two compartments. We have riser, the compartment in which we put gas. Yes. The gas is produced here by cathode because we have a reduction and we have hydrogen. So we have a mixture between liquid and gas. Okay. This is riser. And the other compartment here, downcomer. Okay. And we have junction between riser and downcomer, and we have the surface. Okay. Hydrogen. And we have floc. Okay. And we have induced liquid because we have a difference between this compartment and this compartment. We have only the liquid, we have a great density, and the other we have a mixture between gas and liquid. We have low density, so we have an induction of a flow of the liquid. We have agitation without mechanical power. We have induced agitation only by introduction hydrogen by electric current intensity. Okay, and you have also anode sacrificial, and you have flotation of the pollutant at the surface, and you can remove the pollutant. Okay. The chemicals and the methods. Here we have a special reactor. Our reactor, it's my research. We designed this reactor to have this electrocoagulation. Okay, we put electrode and anode and electrode in the riser. Okay, and we have two parameters. The position of electrodes, it's a parameter. Okay, and another one is the intensity of current. Because if I want to produce more hydrogen, I have to have to increase the intensity by the generators. Okay, and we can measure the liquid by tracer technique. You can measure, for example, by conductivity. You can have measurement of the liquid and the velocity because we have the floc, and to have the movement on the liquid, we have to see what is the limit for breaking this flock, because the flock should be stable. Otherwise, we should search the possibility, the limit of stabilization of the flock. Okay? We use a synthetic dye, dye solution. This is a mixture. As an example, a synthetic dye, yes. And we have to measure the chemical oxygen demand, okay? The decolorization by absorption, the specific electric energy, because we have energy, we have to measure the energy. We have this specific consumption of anode, because the mass of anode should be disappear, etc. Okay? The preliminary test of hydrodynamic and stability of flock. We have to determine the stability of flock. Okay? So measure this is the measurement of by tracer technique. We have one peak for one probe, second peak, and we can measure the velocity of the liquid, because we have time and we have a distance over time, we have the velocity. And we have two positions of electrode, lower position and in the middle position. For the position one, for example, we have a great velocity, okay? And the one, and we have versus the intensity of the current. You have this measurement, we have this, okay? And we have the limit, okay? Another. Next. Okay. This is the limit. We have to use, for example, the velocity that destabilizing the flock is 8 centimeters per second. So we have to manage the current to have a stable flock. This is destruction of flock after 8 centimeters per second. Okay, next. And also we have to talk about pH. pH change during the electrocoagulation. We start, for example, 10 and we finish by 8, for example. When we start for 5, we can reach 7. Okay, the pH change during the electrocoagulation. Okay. Here we have the optimum of a pH, okay. And we have the efficiency here. We can reach 100%. We can reach as a removal. We can reach by conductive, by adding some salt, for example. We can have 100% as efficiency, okay? Now I will speak about the treatment of real wastewater, not synthetic, right? Real wastewater, okay? And we have adopted this methodology. In industry of textile effluent, we have two kinds of dye. We have dispersive and reactive, okay? So in general, we have 3 colors. You have yellow colors, red colors, and blue colors in the mixture. We have 3 colors. And we try to if we can remove 3 or we can 2 or 1, we can see by electrocoagulation what is the limit of electrocoagulation, because there is a limit of electrocoagulation. So you use 3 colors with dispersive and reactive and the mixture, okay? As I say, in industry, in textile industry, we have dispersive dyes, reactive dyes. Dispersive dyes are used for polyester and polyamide fibers, okay? And for reactive dyes, for cotton and viscose. Okay, if you have cotton, you use reactive, because your tissue, for example, if there is cotton, you have reactive dyes. If you have another, you have dispersive dyes, okay? So the electrocoagulation can remove here we remove, for example, almost 100% for the blue and the red one. The yellow one, you can reach only 80%. Okay. This is the yellow one. This is the yellow color. Even is in blue. This is red and blue. This is yellow color. So the yellow is removed less than other colors. Okay. And here, for synthetic reactive, we use iron. It's possible to use iron. Okay. For dispersed synthetic, using for cotton, we use especially aluminum electrode. And the same conclusion, the yellow is less removed than red and blue one. Okay. And for the mixture, the same, we have the red and the blue are more removed than yellow. Okay. And for the mixture, we can reach almost after 45 minutes, we can almost reach 90% as efficiency. It's very important to have this in 45 minutes. In 45 minutes. Okay. And we have here a picture for the airlift reactor. So we have the real textile effluent. After 50 minutes, we decolorize, but the yellow is still is not removed after maybe 61 hours, we can remove all the colors. So the blue and the red is removed first. After that, we have yellow. After I give an example of 15 minutes, but after 1 hour, we can remove. Okay. The blue and the red is more removed than the yellow. Okay. I finished this example of textile. If there is some question about textile here, I will take about the fluoridation now. Another example. Yes. Yes, I can. Yes.
Tes tes. Good morning, sir. First of all, I would like to. The theme is very quite interesting because of Indonesia is full, especially Semarang as well, is full of textile industry, and most of the time the pollution is become a problem. So there's quite a question that I really want to ask on the technique. Most of the time, first of all, is how much durability of the electrode while using the technique? Like how long does the electrode like capable on being used for quite some time? Like is there's like the time when it basically becoming unusable anymore, or it still can be viable for like more than like 24 hour of use? And the next is
About the period of electrocoagulation.
yeah, no,
because you use
the electrodes. I mean the
Electrode.
durabilities,
Yes.
durabilities
Yeah.
on the
Yes.
the equipment. And second of all, is there any guarantee that the metals in the electrode did not like becoming chipped and become like heavy metal pollution? I mean, I'm sorry if I maybe have something here, but I guess that's all. Those are the two. Those are the two questions I want to ask. I guess that's it. That's all, sir.
Okay. Concerning the electrodes. Yes. Consider electrode. There is a Faraday's law. You know Faraday's law. That you can calculate. You can measure the laws of the mass of the electrodes. So you design your reactor That's why we use a lot of electrodes, because if you have the Faraday's law, you can exactly reach the time needed to have, for example, 50% of loss of mass, for example. So we can master this aspect without problem. Okay. The second question, I don't understand the second question. Concerning what? The limits of electrocoagulation.
Yeah, the second question is the metal on the electrodes. Like, is this like consist of like ferron and copper as well? Like, it is possible of heavy metal polluters, like, well, in the water treating. I mean, maybe I could make some kind of a mistake.
In the advantage of electrocoagulation, we can also remove heavy metals.
Oh, I see.
You have remove the cadmium. Yes,
Oh, I
we
see.
can. We can.
So
That's the
basically,
advantage.
so
We can-
basically the metal
because
is not
the
that good.
hydrocidum can absorb all kind of pollutant, all kind of pollutant.
Oh,
And
okay.
we can analyze the flock with the infrared, with the with the scanning electronic microscope, for example, to have an idea about the element removed in the flock. Okay, and you can also measure by absorption, atomic absorption, spectroscopy, the the pollutant in the solution also. And we can deduce that the electrocoagulation is efficient also for heavy metals. Okay. I have a example, but not in this presentation. Okay.
Okay, thank you, sir.
Thank you. Okay. So the second pollutant, fluoride. So defluoridation of drinking water. Now we use water treatment instead of wastewater treatment in a stirred reactor and in external loop effluent reactor. We can have the comparison between the two reactors. Okay. So an excess of amount of fluoride and anion in drinking water cause adverse effects on human health, for example, fluorisis. And the World Health Organization fixed 1.5 milligram per liter as a limit in the water. We have to have less than 1.5 milligram per liter in fluoride in water. In Morocco, unfortunately, there is in some region in center of Morocco, in this region, fluoride contamination is also attributed to underground phosphate, because in Morocco we have phosphate. The first country producing phosphate is Morocco. You know this. The first in the world is Morocco. It's known. Morocco is known by production of phosphate. Okay. In this region, we have also in the phosphate we have cadmium. Problem of cadmium and fluoride. Okay, because when you use, for example, acid phosphoric acid, to have we have little cadmium ppb, but it's not allowed now. We have to remove all cadmium and fluoride in phosphate. That's why we take this. Okay, so we use also electrocoagulation as a process to remove fluoride. Okay. Next. This is the mechanism in general. Okay. And we do kinetic study for you to have an idea about the kinetics inside reactor and in other kind of reactors. Okay. So the kinetics in external is first order kinetics. Okay. This is but in stirred, the real kinetics will be done in stirred reactor, because this is the real kinetics, because we have agitation. Okay. This is more complicated. The kinetics in stirred is more complicated. Yes. This is the apparatus in our lab. So we have some the influence of pH, and there is we expect that the efficiency is more for page 7 than for page 4, but we remark that page 4 is good as it's we expect 7 more than 4, but here we have 4 is more than 7. We have to explain this, okay? Because the pH is very important for electrocoagulation. Okay, next. This is the diagram in which we have, for example, hydroxide aluminum in page 7 is more, but in page 4. For page 4, for example, the fluorescence was nearly complete after 25 minutes for page 4. The most surprising results, for us, it's a surprising results, is that fluoride remains slow when pH is about 7. It's surprising because we expect that pH 7 is more important. As insoluble hydroxide species should be dominant in this region, because in this region, pH 7, we have hydroxide element that is absorb the pollutant. But surprising, why page 4 is more important? So analysis of the diffusion mechanism, Romulo adsorption. We have the question about what about it is adsorption or precipitation? What is the influence of pH? Okay. This is we have adsorption isotherm. Or can okay, we can. The analysis of kinetics is more complicated because we have adsorption. We have to put a lot of equation to have time to have special efficiency. This is the equation. You have time. There is time versus the concentration of fluoride. Okay. This is the model. When you compare this model with experiment. Okay. So the model can match the experiment. The model we use can match exactly the experiment. We have model and experiment. And with this complicated model, we can reach the experiment results, okay? So in the side reactor, the external mass was not limiting. The fluoridation kinetics could be simulated using the variable order kinetics. Okay, a comparison with adsorption isotherm of fluoride anion on already formed flux demonstrate the superiority of electrocoagulation operation over conventional adsorption. Okay, in external, the mixing was less efficient, empirical approach. So the experimental data could be fitted adequately only using up to the first order model. Okay. So we have to understand why pH 4 is more than pH 7. For better understanding of the return mechanism, the sludge protection and composition have been analyzed. We have analyzed the floc and the solution. So here we have the weight of floc. For pH 7, for example, we have a lot of amount of floc with pH 7 comparatively to 4. Even that, we have more efficiency for pH 4 than pH 7. Okay. We have analyzed the sludge with the SEM, scanning electronic microscope, and we have the results for pH, for example, 4. We have the ratio is 0.4. This is the double of in the case of pH 7. Even we have a little amount of sludge, we remove more than when we have a lot of amount of sludge. Okay, that is the results, surprising results. Okay. And we have also the texture of the sludge. We have difference between pH 4 and pH 7. Okay. So the conclusion, the solid phases formed at page 7 are a bit less porous than those formed at page 4 when analyzing the photo of SAM. The amount of fluorine decreases, whereas the amount of oxygen and aluminum increases when pH is increased. The molar ratio in the sludge is 0.44 for page 4, where this ratio falls about 0.25 when sludge weight is multiplied by 2. Derek showed that in both cases, insoluble amorphous compound were formed. There is an amorphous form, okay? Next. And when we use ICP and use the coupled plasma in the solution, we have the mechanism of formation of aluminum. We have increase, decrease for page 4, and almost constant for page 7. We can analyze this. For page 7, a slight increase of soluble aluminum content is observed in the first 5 minutes. Okay? And after a slight decrease, a nearly constant value is achieved after 10 minutes operation. For page 4, a large increase of the residual aluminum concentration is observed, and its value is reached 2070 ppb after 10 minutes. After that, a rapid decrease of this concentration is observed and reach 340 ppb. Is finally obtained after 20 minutes, which is lower than the concentration reported in the case of page 7. Okay? So we can explain, as a result, page 7 particles should be formed preferably in the region of the electrode. The explanation, what is the explanation? For page 7, the formation of hydroxide aluminum is near the electrode, only in some region, okay? So preferably in the region of electrode, followed by adsorption and ion exchange, anion in the electrode. But in the case of page 4, aluminum remain mainly soluble in the first 5 minutes. It remains soluble because should be provided first, not only cation aluminum, but also soluble aluminum fluoride, because there is aluminum fluoride. That's why we have not fluoride in the solution complex. And as fluoride decrease with time, the formation of floccular starch start progressively when pH approach 6. Because even we start with 4, but with time, it becomes 6. That's why, that's explain why initial pH 4 is more than initial pH 7. Okay? Okay, I finished this aspect. There is question. This is to see that it's complicated, the electron. It's complicated. Even it's simple, but the kinetics, when you analyze, we have a surprising result, and we have to explain this surprising result by analyzing the flow, by analyzing the solution, by kinetics, etc., etc. But we can reach you can reach the removal of 100% of fluoride. Okay. Yes, yes. The scale up is easy. Because I work with the semi-pilot and pilot scale. So, because I can reach for example 150 liter to remove as a batch reactor, and I can use as a continuous reactor. The F is continuous in this reactor, for example, is almost industrial. It's a pilot scale, and I can scale up. It's possible to scale up. Okay. Yes, the PhD students have done this. I don't have in the presentation. We have the cost. I don't remember the cost, but we have to minimize the cost by using, for example, instead of the power generator, we use now we will use the solar energy. We will use the solar energy that reduce and the cost also is reduced by agitation, mechanical agitation, because we have induced agitation by electricity, and electricity will be done by solar energy. And we have production of hydrogen. We can have this hydrogen as a source of energy. Okay, so we have 3-in-1. We have removal. We have with free energy, solar energy, and we have production of hydrogen. It's good. Electrocoagulation. I think we can scale up, and we can. I have a project in this way to have this to use wind energy, solar energy, and how to valorize the hydrogen, how to catch the hydrogen. Yes, it's possible. Yeah. And maybe this is, I don't know if I can, well, you have an idea about residence time in a reactor, the concept of RTD, residence time in a reactor? No? Because I use a batch reactor, and now I have to use continuous reactor. And to use continuous, we have to analyze the reactor by the technique of tracer to have if the reactor is ill or not, because there is illness of reactor. For example, dead zone, for example, etc., etc. Okay, our agitation is more important or not. We use this technique, residence time distribution, to study the hydrodynamic circulation. Yes, so I can explain. I try to facilitate the explanation, but I present to have an idea, maybe for the future, to have an idea. Okay, so maybe for me the reactor is many parts of reactor. I have to analyze the flow in each part, the flow, how it is flow. So I use the technique of tracer. So I put several conductivity probes, and I have a tracer, and I detect the history of what become with this tracer, with flow. Okay? So the concept I put here. For example, if I want to analyze all the reactor, I put a tracer here, for example, a salt, Cassel, okay? And I have in the outlet of the reactor a probe. So I put the tracer. I will see if this tracer with we have a continuous flow here, and I will see if my flow is passing by here or by here or by two. Okay, I have to analyze the flow. What is the flow here by analyzing the signal here. So we have tracer and tracer. For example, if the tracer from here takes time to be here, maybe we have two here and here, maybe here. So I have to analyze this aspect. Okay, this is why I do this study to see if this batch reactor can work with continuous reactor, or I have to change this reactor. Okay? Yes? So this is the equation. So the methodology, this is the methodology I just explained. This is the, so we have the signal here in the outlet of the reactors. Our tracer is a direct tracer. We have changing the intensity of the current, 1 ampere, 5 ampere, 2 ampere, etc. Okay, we have the signal according to the current. Okay, but we can analyze this. For different flow rate, okay. And we have the influence of external flow on the velocity of the liquid in the downcomer. We can, okay. Okay, I give the conclusion for this, yes. Next. So, we have two examples. We have, for example, for this, the position is in the low position of electrode, and we have for the current intensity 1 ampere, low intensity, high intensity. Here we have flow rate for liquid, high flow rate, low flow rate. And we have two behavior. The first, we have only one peak, only one peak. For the second, we have two peaks. Okay. So to explain this, that means that when I put the tracer give one loop, one loop, one loop. For this, we have two loops. The first one and the second one. Okay. So the conclusion, this is the, so we have two kind of peaks. We have the first peak. If I have one peak, that means that the flow is by here, 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 one peak. Okay. The second, we have two, because the flow is divided by two, and we have the first peak and the second peak. The first peak here, the second peak. Okay. So, what is the conclusion of that? Okay. No, no. Before. So, for example, here we have the percentage of flow leaving directly before, please. The goal is to have the flow passing by the riser, because here we have the electrodes. Here we have no electrodes. If the flow pass by here, it's not interesting because there is no electrocoagulation. The coagulation will take place because we have electrodes here. So I have to have the flow by here, not by here. Okay. So the conclusion is this reactor is not good for continuous mode. It is good only for batch mode, because maybe 60% quit the reactor without reacting, because the reaction is here. Here we have the flow keep 50, more than 50% quit the reactor without reacting. So it's not good for continuous mode. It is good for batch mode and not for, that's why we reach another configuration. Okay. 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 So I finished this part. So the conclusion, this type of reactor, we choose external lifters, is good for batch reactor, but not good for continuous. That's why we simulate another reactor. We can design another reactor with simulation. And with simulation, we can improve the configuration of reactor. We can improve, okay? Donc, rapidly. Next. This is the modeling, the software for modeling, etc., etc. Okay, we can. Okay. This is more. You can. Okay, okay. Okay. Yes, yes. This is a simulation. My reactor in batch that works or in batch was simulated. Also, we have this simulation, okay? And we have some results, okay? Okay. I give also yes, the results. Yes, yes. Okay. Next. How to work? This is the simulation. How the flow works. Okay. This is the electrodes. This is the hydrogen simulation of the hydrogen and how it works. Okay. Okay. You have an idea about the production of hydrogen. The liquid is stable here, for example, is stable because the blue is 0. The red one, this is the gas. This is the presence of gas. Okay. That's why we have another configuration. Another configuration. This configuration is better than the other one. Okay. This configuration is better than the other one. Okay. And we have some results about simulation. Okay. You have an idea about the production of hydrogen, etc., etc. Okay. Okay. So the simulation revealed the importance of current intensity and electrodes position. It's confirmed by simulation. The position is very important. The position of electrodes in the downcomer is very important. And average liquid increase when the electrodes are positioned in the depth. Okay. This is confirmed by simulation. Average liquid velocity increase when bubble velocity increases, and average liquid velocity decrease when the bubble diameter increase. So we have the details of the movement of the liquid by simulation. The outlet position can also influence the liquid velocity. Okay, next. Yes, that is to reply to your question. We have conceived a pilot external with 115 liter, according to the simulation. Okay, we have the picture, we have the design, and we have also, this is a reactor, 150 liter to realize, for example, the textile effluent electrocoagulation. Okay. And we can give an example. For this, we have tested the textile effluent in this reactor. No, before. Using iron and aluminum at the same time. Okay? And we have reached, for the real textile, 80% for efficiency. Okay? And here we have the energy consumption. As I say, they have reactive, dispersive, and mixture. When we have the mixture, it's less consuming the energy. Okay, I reduce the energy by the mixture of reactive and dispersive. It's more important to remove all in the same time, the mixture. Okay, and we can reach 80%. And we have some to analyze this. Okay. We have the SAM, okay, and we have the results here. In the flock, we have detected the presence of aluminum and the iron. That means that both electrodes participate in removing the color, both, because we have iron electrode, both are sacrificial anode, because presence is here. Okay, Okay. And in the solution, we have respecting the standard, Moroccan standard for aluminum is 10 milligram liter, and we have only 1.80. And for iron, the Moroccan maybe in the world it's less than this, but in Moroccan it's 10 for aluminum. And for iron, it's allowed to have 3 milligram per liter in the solution, and we have on that almost 2. It's less than. We have respected the Moroccan standard concerning this aspect. Okay. So the conclusion, the final conclusion, electrocoagulation, electroflotation has been successfully realized in a pilot scale here. External loop airlift reactor to achieve a complete flotation. We have achieved a complete flotation with good mixing and used by only teeny bubbles generated electrochemically by water electrolysis. The treatment of the effluent in this continuous reactor doesn't therefore require a separate filtration. We don't require the filtration because we can remove the flock, okay? Since the flock which is formed in the free surface on the reactor can either be scarped or recovered by simple overflow, okay? The performance obtained for the stirred electrode, the stirred reactors are the same as the external, are the same. The advantage of electroflotation in external is that the electrical energy cost is offset by the lack of the mobile, mechanical, or pneumatical for agitation. We don't need mechanical agitation. With the advantage of the lack of filtration, that is an investment and the cost non-negligible maintenance. Okay. Next. Thank you. Is it correct? I finished my first presentation. Yes.
Thank you, Professor. Good morning. My name is Fauzi from Environmental Science. Maybe I will ask about electrocoagulation. The problem of the coagulation process in general that I know is producing sludge which is dangerous and toxic waste. Sludge which is dangerous and toxic waste. Toxic. Sludge which is dangerous and toxic waste. Toxic waste. Sludge. Dangerous waste. Sludge which is dangerous. Coagulation process in general producing sludge and the sludge is dangerous or toxic. Meanwhile, the electrocoagulation process does not add chemicals. So does this mean that the sludge residue produced from the electrocoagulation process is safe and not considered in toxic waste? And second question, in your presentation, the electrocoagulation process can destroy certain bacteria. Therefore, is the biological process after electrocoagulation process is still needed? And yes, it's my question.
Before we focus in eliminating ruining, that's all. But we have to break the task, waste also. Actually, I don't know why the future of the sludge stop the sludge, because we have already. This is the first one. Second, bacteria.
Yes, bacteria. So, so biological process is still needed or no after electrocoagulation process? After electrocoagulation process, is biological process is still needed or no? Is still need? Is still needed or no?
Maybe we have to use hybrid process because right now I use electrocoagulation and electrohandling. We can use other process, not only electrocoagulation. For example, high quantity amount of pollutant, there is limit of electrocoagulation. After electrocoagulation, we can use electrohandling or other technique, maybe flotation, ionic flotation, as I will present. So in general, for the process, we use not only one process. We can use 2 or 3 or 4 to have a complete removal. And concerning the such, it's how you have to manage this. Therefore, to have the economic circular economy.
Thank you, sir.
Is it new for you or new? Some concept? The second one concerns the ionic profesor. I don't start now.
Oh, maybe there is a question from the online participant. You can raise your hand for the online participant, or you can put the question on the chat.
Yes, yes.
Wastewater jewelry, in
What?
jewelry industry.
Okay.
But it's combined with the biological, such as wet lab
Mm.
and absorption.
Absorption.
But I'm not that expert in this.
In absorption.
Something,
Ah,
yes,
yeah,
but,
yeah. But we have to work with the other segments. Yes. Thank you. Okay.
maybe if
This
Mr.
water.
Mariano, oh yeah, maybe if Mr. Mariano is
This
too
water.
long,
Yeah. Okay. Ah.
yes. You don't have like this in one. You have like this.
No, no, no.
No, it's in bottle.
In bottle. Yeah. In bottle. Yes. Next, yes, next. We start. We're with you to start. No, no. I can, yes. Yeah. So the second presentation, uh, so the second presentation is about or ionic flotation of zinc and iron as an example, but we can use other metals in a rectangular, a special cell flotation, rectangular bubble column. We studied the hydrodynamic and kinetic study. Okay, this is an example of a PhD topic with my student. His name is Uthman Tigri, PhD student, his work, and myself. Okay, this is an example of a PhD thesis, how to to manage this topic. Okay, so the plan, a brief introduction. I will talk about experimental method and the kinetic study. After that, the hydrodynamic study, why hydrodynamic is important for flotation, for a process, because this is why the chemical engineer approach is very important for environmental research. It's very important to have this tool to optimize, to comprehend, to etc. And a conclusion, okay? So it's obvious that many industries release pollutant in the wastewater containing high concentration of heavy metal. There was a question about heavy metals, yes? Metals and heavy metals. And we have a lot of methods to remove these metals, as for example, chemical precipitation, ultrafiltration, electrodialysis, solvent extraction, reverse osmosis, ion exchange, adsorption are commonly used for this purpose. But ion flotation may be an alternative method to remove heavy metals, ions, from wastewater because it's simple and low energy requirement. You will see that it's very simple, this process, very simple, and low energy requirement. Don't require enough energy. Okay. Next. Okay. In the mineral fields also, not only for environmental aspect, but we can have, for example, the gold or mineral, copper, zinc, etc. Okay. What is ion flotation? I give the definition of ion flotation. What is, you have an idea about flotation? Ion flotation? No? Flotation, we use flotation to remove from solution. Okay. So we need for this two compounds, surfactant as a collector and bubbles, gas bubbles. Two compound to have the, okay? So I give an expression. So you need a surfactant or collector, okay? This is an example of a surfactant. I call this surfactant SDS, okay? We have two compounds. We have this compound is, we have carbon, carbon, carbon. This part is hydrophobic part. This part hates the water, Okay, and we have this head love the water. This is hydrophilic part, and this is hydrophobic part. Okay, this is the collector, this is the surfactant. We need this. Because we, as I explained, we have 4 kinds of surfactant. Anionic with negative, cationic, positive. This head can be, for this example, this is negative because we have Na+, this is negative. We have cationic, we have non-ionic, you have amphoteric, zwitteric, that means we have 2 heads, one cationic and one anionic, okay? And we have also need the bubble. So we have the bubble and we have the surfactant here. Because this part is hydrophobic, they quit the liquid, the water, and can be absorbed into the bubble because this part hates the water. So it is absorbed. And we have this head, this is negative parts, hydrophilic. That's why this is in the side of the water, okay? Because he is negative, and we have the cation, for example, zinc, iron in the form of the cation. So we have negative with positive. We can, for example, for the iron positive with the negative part, we can be attached, forming a compound. So we have this part, and this part is attached to the bubble, and the bubble flotate. Donc we can remove by collector and the bubbles. It is clear. I think it's clear. Okay. So I said that we have a hydrophilic head and hydrophobic tail. This is the surfactant in general. Okay. We have 4 kinds of surfactant. Non-ionic, there is no ion. Cationic, anionic, and amphoteric. 2. We have cation and anion in the same time. Okay. And we need, for our case, ionic, we need this because we have the zinc as a cation, iron as a cation, etc., etc. We need this part. Okay. This is sodium dodecyl sulfate, SDS. Okay. This is the principle, and to have the surfactant have 2 main characteristics, what we call critical micellar concentration, CMC, because you have micelle, formation of micelle here. With low concentration of collector, as the collector hates the water, he is in the surface because he hates only this part touching the water, but the other part in the air. Okay, but after saturation, we have some collector here, and they have to, because they hate, and the hydrophobic part is here, and forming the micelle, and the minimum concentration is the critical micellar concentration. So the CMC for critical micellar concentration corresponds to the concentration of surfactant in a medium from which micelles form spontaneously Below this, the surfactant forms a layer on the surface, on the liquid, and the rest is dispersed in the solution. Once the CMC is reached, the surface becomes saturated with surfactant, and the new molecules group together in the solution, forming micelles. This is characteristic of micelles. That's why when you have some dirty in your tissue, you use detergent. This is surfactant that solubilize your lipid compound of your dirt. Okay. This is the first characteristic. The second one is what we HLB. That means hydrophile lipophile balance, because we have two parts: hydrophilic part, and hydrophobic part, and we have to see what is the dominant. It is the hydrophobic, lipophilic, or hydrophilic. We have an index between 0 and 20. If, for example, HLB index is less than 8, that means that the amphiphile, or surfactant, is lipophilic, is more lipophilic than hydrophilic. If the HLB index is greater than 12, the surfactant is hydrophilic. This is a balance, it's sort of the measurement of the character of hydrophobic or hydrophilic. Okay? First, next, please. So the objective was of the study is to comprehend the mechanism of ionic flotation in order to master the selectivity. Because in solution, we can have a lot of metals, for example, copper, aluminum, iron. If I have the possibility to select, for example, to have only iron without aluminum, it will be good. For example, if I want gold as a noble metal, I don't want, for example, iron. If I have a special collector, surfactant, to have only the gold instead of other metals, it will be very interesting. This is the goal, but it's very difficult to have this. This is the goal. But we can, if you comprehend the phenomena, we can reach this goal. Also, to optimize the process, if I can only put the minimum amount of the collector, it will be good. And the minimum of bubbles, because we need the collectors and the bubbles. That means I have the gas flow rate is minimum. So the energy is less, and I can minimize the energy. This is our objective. So the conception of a cell flotation, we have used a semi-pilot reactor to have the solution. And I need to realize the fine bubble, but because in flotation we need fine teeny bubbles, not large bubbles, because it does work with large bubble. It works with teeny, very teeny. In order for example, if I can 50 micrometers, less than 50, it will be good. Less than 1 millimeter, it will be good. And I use for this the centered glass, because the glass we have the porosity, and when I put the gas become small bubbles into this is the centered glass, and I have small. And in the surface, we have the foam. We recover the foam with the metals and the collectors. Okay. So we put some probes, pressure probe. I will explain why I put pressure probe. Okay. So the quantity is the capacity is 6 liters. A small cell, but not very small. 6 liters, okay. And we have the design, and we have realized this flotation cell with here the pressure probe to measure the pressure here and the pressure here, to have an idea about the gas, the quantity of gas. I will explain how. Okay. So this is we can measure the flow rate of gas by this flow meter, okay, and we have also the pressure probes. Yeah. This is an example of the presence of copper. This is copper. The blue one indicates the copper. Okay. And for analysis of solution and foam, we have to analyze the solution and the foam. Okay. For this, we use atomic absorption spectrometer. Okay, to analyze the solution, if there is metals or no. Okay, we can measure zinc, iron, aluminium, as cadmium with this atomic absorption spectrometry. This is apparatus. Second one, this for measuring the tensiometer, surface tension of the liquid, because there is a difference between water and water with surfactant. Water with surfactant, the surface tension is decreased with the that indicates the presence or not of the surfactant with this apparatus. Okay. The technique is the hanging drop. We have a hanging drop. We have a camera, and with this the shape of I can measure the surface tension of the liquid. For example, for the distillated water, the number is for surface tension is 72 millinewton per meter. If I add a little amount of surfactant, this 72 become maybe 40. That's indicating the presence of surfactant. For example, I can tell you if there is water or not. If I measure, if I found 72 millinewton per meter, this is water. But if I found like 60, this is water plus something. If I have the tensiometer, I can before drinking, I can test if very is water or not, because little amount can change surface tension. With some detergent, for example, that can decrease the quantity. And we have this apparatus to measure the quantity of surfactant. Okay. And we can recover after flotation. We can recover the foam. In the foam, we have the metal, because the metal was in the solution. And I put the collector and the bubbles and floatate in the form on the foam. And I can dry this foam in our oven, 100 degree, for example. For example, I give an example of iron solution. After that, we have normally the iron here or zinc. After drying this, we have this foam become in form of powder. For example, the dry foam containing zinc. This is the color of zinc. Okay, this is the color of iron. And when we have the mixture of zinc and iron, we have this color. Okay, and I can analyze this by infrared transform the Fourier transform. Okay, I can analyze this to have an idea about the foam, the containing of the foam. Okay, and this is the Fourier transform infrared. Okay. Now for the bubble the diameter, I need to know the size of the bubble. For this, I use camera. I use a camera here, and I can record with a rapid camera. I can, for example, 10,000 frame per second. I can record, and I can slow the motion, and I can see the velocity. I can see the size. But I have to analyze this by a software. It's not easy to measure directly by viewing the camera, but I have to do a software, not a software. Okay. And you can use, yes. for this, okay? This is distilled water. We don't have the film because we don't have movie. I touch. Yes. So there's a comparison between a liquid absence of collector. Do you have this, the size of the bubble here? Yes. Yes. Yeah. Yes.
In my home, and maybe this is just start, but I interesting to understand when we make eco enzyme from the waste fruit,
Yes.
and then we put, and then maybe one day, day 1, day 2, day 3, day 4, and then there's some bubble like reaction,
Yes.
chemical reaction,
Chemical reaction. Yes.
and then some part of maybe they have some, I put some how to say to transfer the gas
Yes.
and to this and then I try to put in the maybe aqua, and
Yeah,
then,
yes, yeah.
and then I can show the bubble.
Yes.
Sometime the gas
Yes.
is active and bubble so many, but sometimes no bubble and no gas.
No bubble.
No bubble, no gas. But
Okay.
if I, how to say, maybe this is just another case, but it is the same. What do you think about the how to say, the impact of bubble, many bubble or not so many bubble, and according to the chemical condition that we would like to reach, maybe this is stabilize component or not?
For example, the bubble, for example, the air bubble
Yeah.
contains the oxygen.
Yeah.
And the oxygen quit the bubble to the liquid. And there is a reaction after mass transfer. That's explain. And the size of the bubble is very important because if you have large bubble, the large bubble have the high velocity, they quit rapidly. But that's why we choose the fine bubble, because the fine bubble slowly, and we have time to have reaction or flotation or someone. Okay? So,
I just start for this one. So sometimes I make a joke with my student.
yes.
This is the Japanese language. Leputuk gitu ya. Maybe this is because this is a bubble. What do you think about many bubble or not many bubble content to the, what to say, the condition that maybe
We prefer many bubbles. We prefer bubbles. To maintain the bubbles, we have to master the size of the bubble. It's very important. What we call hold up, gas hold up. Gas hold up should be higher because the quantity of gas should be in the solution, the liquidity. Don't quit rapidly the liquid. Yes. Yeah. Yes. And you can. No, this. Okay. No, yes.
This is the diamond bubble. This one.
Here or?
Yeah, this is one. This is the bubble. That is it. This is the small.
Small, very small. Yeah.
Okay, continue.
Before. Yes. This. Only one. This is an example of distilled water. So we have no foam, and the size of the bubble is relatively large, and here we use surfactant. That's why we have, you can put, okay. You have fine bubbles here comparatively to this, and we have formation of foam because the presence of surfactant. This is the difference, okay? And we can recover the foam. And here we have an example of iron, how you can, we have iron collectors and water, okay? You have iron here. You can remove the iron, okay? That's all, okay? So for the bubbles, the history of bubbles, we measure what gas hold-up measurement, okay? By using a technique of manometric method, by differential pressure, we can measure the quantity, the amount of gas by measuring the pressure, because the pressure change when the gas change, the flow rate change, because we have liquid, and after that we have liquid plus gas, and we can measure the percentage of gas by measuring by this technique, by putting the pressure probe, okay? For that, we have the pressure probe. Here we have the pressure probe, and we have the acquisition card to have a signal for pressure to measure the pressure, okay? And we can have a relationship between the presence of gas, this is the percentage of gas, 5%, 10%, with pressure drop, P1 minus P2, okay? This is the density of liquid, G, 9, and the distance between the two probes. So you have an idea about the quantity of gas. This is important for flotation, okay? And I show you some example. The parameters studied are pH is very important in this process, and the gas flow rate, the two, and the third parameter is the ratio between the presence of collector, the concentration of collector over the concentration of metals. Okay, we can have this ratio 1 or 2 or 3 or 4 or 5. You have a small amount, little amount, great amount of, and we have C. What is the solution of this? Okay. Here we use as zinc, the source of zinc. We use this the source of zinc to have this cation. Okay. We proceed to analyze the foam by infrared. Okay. The infrared measures the vibration of the group. Okay. I show you an example of infrared, for example. Okay. Here, I put the powder of only the collector to have the signal of the collector, only the collector, and I compare this powder with the foam, the dried foam. I have the same signal. That means that in the foam, we have the collector. That means that the collector floates to the foam. Okay? This is well, the same. Okay. Okay. We have the same. All time you have in the foam, we have the collector. That means that the collector is the foam. But we can't conclude that the presence of the collector in the foam indicate the presence of metals. Maybe the collector with the solution without metals. Maybe. Okay. So I give you some results. Okay. This is important for zinc. I start with pH 2. 2, acidic. Okay, acid. I can conclude with the ratio 2. That means that the concentration is the double of the zinc 2. I have constant efficiency. Even I increase the, or please, even I increase the number of bubbles, it's still constant and not reach 35. It's low efficiency. Okay. But if I add some amount to have 5, I can increase. But I still with the 70%, only 7, not 100. Okay. After 1 hour, this is 1 hour. I have only here. I have 35. It's not good. And here I have 70. It's good, but not enough. Okay. So I have to change this page. It's not good for me. Okay. I have to explain why page 2 is not good. Okay. That's why I use another. So for to conclude, for a low concentration of surfactant, this is a low concentration, the efficiency is low and doesn't depend on the quantity of gas. Even I put a lot of gas, still constant. Okay. For a sufficient quantity of surfactant, 5, the efficiency improves and increases with quantity of gas, but doesn't exceed 65%. So we can conclude that for an acidic pH, I have to explain why. Because there is selectivity for acidic pH. We have the presence of H and ions, and the collector prefer anion than zinc. That's why this is a constant. So the strong presence of it competes with zinc. Okay, the probability of metal recovery increase with increase in the number of bubbles if the surfactant is very sufficient. That's why I have 65%. So I choose another pH to improve my efficiency. I choose, for example, pH, okay, 6. Okay. The same time, by infrared, I am sure that the surfactant is present in the foam. This is okay, and we have the SRM. I can have an idea about the presence or not of the zinc. Okay, I'm sure the zinc is in the foam because there is presence of zinc. There is presence of collector and zinc. That means that the flotation work. Okay. Same time, I have all the zinc in the foam, dried foam. Okay, and I improve the results. I can reach almost 90%. Okay, 90%, but after 80 minutes. Okay, 1 hour and 20 minutes. I can reach with several ratio. Okay, so I improved by page 6. Okay. Now for the iron, I use only zinc. Now I use the iron. The results, the same results. I prove that the existence. I prove the existence of iron in this foam. Okay, and I can. Okay, you can conclude. Only 25 minutes. I have almost 100%. So the iron is more removable than zinc. For zinc, I need 80 minutes. For iron, I need only 25 minutes. So there is a difference between iron and. I can explain this by the charge, because the zinc we have 3+. So you need three collectors for 1. For iron, I need 1 collector for 1. Because I have plus Fa or H plus, so I need 1 collector for iron. But for zinc, because 3 balance 3, I need 3. That's why the efficiency for iron is more important. I can reach almost 100 only for 25 minutes. Next. Okay. 2, please. 2. I need 2 for 1. Before. 2, please. I need 2. Here I need 1. Okay. So I can, now I put together zinc and iron to have an idea about the selectivity. The collector prefer iron or zinc or two, okay? The same, I, systematically I put the infrared to have an idea about the presence or not of the collector, okay? Same, systematically. This is efficiency. We have iron and zinc. Iron with read, zinc. Before 30 minutes, there is selectivity. We have the efficiency, for example, of the iron is high comparatively to the zinc. But after 30 minutes, it's the same. So the selectivity works before 30 minutes, after 30 minutes, it's the same because we have enough collectors. Because after that, we have enough. Okay. So we have an idea about the selectivity in time. Selectivity before 13, after what we have the same efficiency. Okay. Let's see what surface tension indicates. Okay, this is the measurement of the surface tension. It is an indication of the presence or not of the surfactant in the solution, because if there is only water, we have what is the number 72 millinewton per meter. If there is surfactant, we have less than 72 millinewton per meter. This is an indication of presence or not of the collector. Okay. This is to measure the CMC. Oh, okay. Okay. I explained this figure. We have an increase of over time. I put the sample and I measure every 5 minutes. I measure the surface tension. I can conclude that the surface tension increase with time. Because I have, for example, here 62 or 61, and with time we have almost 72. That means that the collector quit the solution, and I have the same character of water, only water, without collector. That means that the collector quit the solution. This for zinc, also for iron, and for only collectors. Okay, this is an indication, and I can use the tension surface tension as an indication of the work of the flotation, if the collector is still present in the solution or not. Okay. So from this curve, we can conclude that the surface tension increases with time to approach that of distilled water. Okay. This may indicate that the collector responsible for the decrease in the surface is increasingly recovered with time in the foam. Okay. Now, what about hydrodynamic, the presence of gas? Okay. I explained epsilon G is the percentage of gas. For example, if I give some comparison, for example, distilled water. For distilled water versus flow rate, for example, this increase but is less than, for example, tap water. Tap water, we have more gas than distilled water. If I put the flow rate, we have more gas in tap water than distilled water. And I have more gas when I put some surfactant. The surfactant increase the number of gas, increase the number of bubbles. This will be an indication also for the presence or not of surfactant. Okay. And I have an idea about epsilon G with time, the decrease. That means that the collector quit the solution, because the presence of collector in solution increase epsilon. If the collector quit the solution, that decrease. Okay. So I conclude, this is an example of the presence or not of the collector. Without collector, we have this picture. We have to analyze. We have some size of the bubbles. We can have an idea about the size of bubble. Here we have the teeny bubbles. We put SDS as a collector. We had that teeny. It's difficult to have an idea about it. We have to analyze by a special software, okay, to have an idea about the bubbles, okay. Also, and there is the conclusion with surface tension, with the efficiency of atomic spectroscopy, and with the presence or not of the gas, okay. So the conclusion is, we can conclude that the iron in our work recovery is faster than zinc. We have to explain why. Maybe for the chemical structure, okay? And the recovery of zinc or iron is greater for pH 6 compared to pH 2. So the pH is very important for flotation, okay? Close to the neutral than an acidic pH. And the surfactant recover more iron than zinc for the mixture, for the 30 minutes before 30 minutes. And for the perspective, the image processing is to be developed to quantitatively determine the size of the bubbles is important for us. And the complete hydrodynamic study should be continued with CFD study with simulation. Thank you. If there is some question.
I just want to know about the software. Can you show us the software or the tools in this year presentations? And then I just want to know how it works to the to measure the velocity, to measure the to measure the diameter of the bubbles resolved by the surfactant in the reactor. Thank you.
For this, we have used a rapid camera, and we can record the camera, and we can see the velocity. The velocity, we can measure the velocity of the bubble. But the diameter is very not easy to measure. We have to analyze the image by a special software to have an idea about, but it's not easy also, even with software, because with the weak flow rate, it's possible to have, but great flow rate, it's very hard. We have to use a special and specialist for image processing.
Oh, special.
It's not our domain,
Okay.
but we have to work together with other researchers.
Okay.
It's not our domain, but we have the research. We have to work together.
Okay, good.
Different specialty. Okay.
Thank you. Because I just read the article that discuss about the velocity and the tools, and there are a lot of the tools.
What you mean by periodicity?
Velocity?
Yes.
Velocity.
What
And
is the periodicity?
I really don't. This is new for me.
Yes.
So I just read the velocity. You said for the velocity, the density of the what we call it, the bubbles. I just read on internet that there are a lot of the tools or the software used by the researcher for measure the bubbles diameter, the velocity, and I just want to know what kind of if possible, you can show us the picture of the tools or the software you use in your research.
Yes. For flotation, I need the bubble diameter or the size of the diameter, because maybe the bubble is not spheric. Maybe it's have another form. Okay. The size of the bubble. Okay. I need the size of bubble diameter, because if there is the bubble, if the bubble is small, is in general is spheric. Is spheric in general. So I need the bubble diameter. I need the velocity of the bubble, I need the number of bubbles. Three parameters. So for the number, that's why I use the pressure probes that indicate the percentage of the gas. And the percentage of the gas with the diameter can give me an idea about the number of bubbles. The number is important for me because each bubble can remove, I don't know, 100, 1,000 metals, because you have one bubble. For one bubbles, one bubbles can be recovered by 100 or 1,000, I don't know. That's why I need to know the number of bubbles, the velocity of bubbles, and the diameter, not the periodicity. Periodicity is not, for me, that means nothing for me. What periodicity for me, nothing. It's question of bubble diameter, number of bubbles, and velocity of bubbles, because the velocity is important to have. I need the slow velocity to have time to recover. If I have the velocity that quits immediately the solution without flotation, okay, I have to master this aspect. I have to master this by different techniques. For example, camera. Maybe there is a sophisticated technique like laser, like fiber, optical fiber, maybe tomographic technique. There is sophisticated, but it costs. It costs. Okay. So that is the topic of to comprehend the flotation and the selectivity. Why, for example, why the collector prefer iron than, for example, zinc? Why? To comprehend this, and we conclude that before 30 minutes, the iron is more recovered than zinc. But after that, we have the recovery of the both metals. Okay. Questions? So we have two techniques. So for Roman, we have electrocoagulation, we have flotation. Is there any relation between electrocoagulation and flotation? According to you, is there any relation? Or can you, your question was about someone, you? About the limit of electrocoagulation. Yes, the limit of coagulation. There is a limit of coagulation. After coagulation, we can use, for example, ectophantan. We can use also, maybe, ionic flotation. What is the relation between electrocoagulation and flotation, for example, according to you, or your view? Any idea, it's accept.
First of all, because of this different technique than I ever experienced to see it. Because my background is coming from biology, so therefore it's kind of hard to be. But well, I'm trying to do my best to what's it again, to introspect the whole.
But for example, for this example, I have to remove, for example, iron. For example, I can remove iron by ionic flotation. Okay. But I can remove iron by electrocoagulation. But in electrocoagulation, we have the sludge, and the sludge, there are a lot of pollutants. Here we have the foam. It's easy to use the ionic flotation than electrocoagulation. Okay. But if you want to use, for example, electrocoagulation and ionic flotation, there is a relationship. There is a intersection between electrocoagulation and ionic. Concerning what? Because in electrocoagulation we have sacrificial anode and cathode. At the cathode, there is what? Production of what? Hydrogen. Hydrogen is a bubbles. And we need the bubbles for flotation. You see, I can use the hydrogen is more perfect than gas, than air gas. Is teeny bubbles, and I can use this hydrogen for ionic flotation. I can use this. Okay.
This is another thing. Do you have any experience about how we control the water from aluminum and magnesium? What do you think about this? And you think?
The aluminum as pollutant?
Yeah.
Yes. Yes.
In Indonesia, we have yellow water because this is content of zinc and also maybe content of aluminum.
Mm-hmm.
And maybe this is very hard to remove in the
Aluminum.
yeah.
Why is
What do you think about how we control all this?
we can use also the electroporation.
Do you have any experience?
Yes, yes, yes. Yes, we can use the electroporation as a process to remove aluminum.
Do you have some experience how much cost for this in
The cost?
industry?
The cost, I have a study with cost, but I have not in my presentation. We have because we want to optimize by reducing the cost. I don't have the number, but we can. For optimization, I use innovative reactors, and I use renewable energy, like solar energy and wind energy. I want to use this to reduce the cost. Because the cost is the electricity, and the cost is the material, because anode sacrifice, you have to change the energy. This is the cost. But I gain because I produce hydrogen as a source of energy, and I can have the energy for free. Solar energy, for example, I can reduce the cost of the electropopulation.
Okay. Okay. Go to the next or
5 minutes.
oh yes.
It's hard.
This pipe.
could have maybe wire.
Okay, I can start.
Yeah.
Start the presentation. Yes. Okay. The third presentation is about bubble forming. Bubble forming. So I read the picture of our laboratory. 4 meter high, okay, and we have the curve, the curve, not before the presence of the sunset pattern. But the fact is the effect of quality and low quality water organic mixture on hydrogen and mud transfer. Mud transfer. Why we use bubble form? For example, for environmental engineering. To treat what? What kind of pollutant, for example? You can treat the pollutant with the bubble column. For example, you have the opportunity. How can we can, for example, treat the gas pollutant? By which technique, which process? The gas, toxic gas, monoxide carbon or dioxide carbon. How? By absorption or absorption. You have to put the gas into the liquid. Okay. Absorption. No? This is a technique of it. That's why we use, for example, the bubble pump. Okay. So maybe I can give you some idea of this, but these are important and these are important for the gas treatment. We have to use the gas treatment function. Because the politics the politics, for example, the gas, when we put the gas into the liquid, the gas becomes bubbles. And we have, for example, toxic gas must quit the bubble into the liquid. And outside we have low concentration of gas, okay, because the gas is into the liquid instead of keep quitting in the air. Okay, that's why we use the bubble. Okay. So ability of understand that the reaction after formula in bubble form. Can we do reaction, chemical reaction in bubble form? Reactive, for example, gas and other reactions in liquid, and we have reaction between gas and liquid. But we do this in bubble form. Okay? The mass transfer phenomenon is very important. The gas liquid transfer coefficient is related to the bubble characteristic, turbulence, and the bubble reaction. It's complicated. The head element is very complicated because you have liquid and gas in form of bubbles. You have to study what is the meaning of hydrodynamic. Okay, because of the complexity of the interaction dynamic parameter in the hydrodynamic, the experimental approach consisting using rubber, gas bubble, is still used because we have to know the amount of gas in the bubble form. Because the bubble is large, the amount of gas is not the same in each zone. For example, in this zone, we have a lot of gas, here, few gas, and so on. So have to measure in each zone what is the amount of gas. Okay. objective, identify the regime transition, because when we put, for example, the gas for low flow rate, we have little bubbles, okay? We have what we call homogeneous regime, because the size of bubble is the same, we have the same size. When we increase the flow rate, we have the coalescence. What is coalescence? If you have a lot of bubbles, the bubbles with two bubbles with bubbles coalesce to form one bubble, and the velocity increase. This is coalescence. Okay, this is coalescence. You know, I have to know what is the limit between homogeneous and heterogeneous regime. Okay, this is a hydrodynamic study. How to see for flow rate, which is the transition between when I have the same size and we have a lot of size because of the coalescence. Bubble plus bubble, another bubble, other bubble, large bubble, few bubble, teeny bubble, etc. This is heterogeneous regime. I have to see the limit or the transition between homogeneous and heterogeneous regime. For that, I use, to have coalescence, I use okay. To increase the viscosity, I add some subcompound, CMC, to have coalescence. Okay. This is the apparatus where I put a lot of probes, pressure sensors, to have an idea about the presence of gas. Okay. In this zone, and the overall zone, I can have an idea about the gas in each zone. Okay. And also, I use conductivity probe to have an idea about the hydrodynamic by the Trasher technique, for example. And I put also an oximeter to have the presence of oxygen, because I use the oxygen as element of mass transfer. I have to measure in this region and in this region the mass transfer of oxygen into the liquid. Okay, so I have 1, 2, 3, 4, 5, 6, 7 probes with a system acquisition, and I can see all in the laptop. I can see the signal of this pressure, conductivity, in the same time. Okay, I can measure in the same time the presence of oxygen in the liquid and the quantity of gas in the liquid. Okay. So we have this pressure probe with acquisition system, and we power this electrode with a special design, printed circuit board. Okay. For the hydrodynamic study, I use surface tension, because I can use alcohol. I add alcohol to inhibit coalescence. And when I use, for example, carbomethyl cellulose, I can increase the viscosity and can measure the viscosity and the rheology by a viscosimeter or rheometer. I can use this to have an idea about the characteristic of the liquid, viscous or not. Okay. As the bubble is large, because the height of large is 4 meters, I have to divide the column into 2 zones, or 3 zones, or 4 zones. I use 2 zones. So 2 gas hold-up was measured, covering zone 1, the lower zone, and the higher zone. Okay, and the overall gas hold. Okay. For non-coalescent system, I use alcohol. If I don't need the coalescence, for example, when I use the surfactant, there is no coalescence. When I use, for example, higher viscosity without surfactant, I have coalescence. So I start with no coalition system. I use bicameral. Liquid bicameral. Okay, with this coalition. I have tiny bubbles. And I have an idea about the presence of gas. The presence of gas. Now, I should the gas flow rate. I can reach 20% of gas. 20% of gas by using bicameral. Okay? It depends on the zone. In the lower zone, we have the presence of gas is less than in this zone. The bubble, the number bubble, the bubble increases with the position of the bubble. Okay? Because of the division of volume. This is an example. Okay? These are comparisons between water, ethanol, propanol, ethanol. These are examples. You have a small amount of, for example, ethanol, propanol. I can increase or decrease the presence of gas. For example, for water, here. Because there is a coalescence, because the gas quickens rapidly. When I put small ethanol, the gas increase, the number of bubbles increase. When I put propanol, increase. When I put ethanol, increase. So a small amount of alcohol, depending on the number of carbon, we have 4 carbon. 4 for propanol, we have 3, and for ethanol, we have 2. Ethanol, 6, propanol, 6, ethanol, 6, 4. But I put more carbon, I can increase the number of bonds. I can increase the number of bonds. Okay? The explanation is because the butanol, ethanol, propanol behave as a surfactant because we have hydrophobic part, hydrophilic part. It's the same as a surfactant, and I can explain why. When I put more carbon for surfactant, I have more gas. I can explain by the same way as flotation, ionic flotation. Okay. For coalescence system, so for coalescence, I don't use alcohol. I use other thing. I use carbomethyl cellulose to higher the viscosity for favorizing coalescence. For this, yes. For example, I have 7 grams per liter, and I have the quantity of gas depends of the zone. In the higher zone, we have more gas than in the lower zone. Okay. And when I compare coalescent and non-coalescent, for example, for butanol propanol, we have more than 20% of the gas here. Here, for example, for only water, I have only 15%. So we have a difference between 5% difference between coalescent and non-coalescent system. Now for mass transfer, how to measure the mass transfer? We put here the oxygen probe, okay? Here, for example, I put the oxygen probe, okay, to have an idea about the concentration of oxygen in the liquid, okay? And I have to measure the oxygen concentration at a position 1 meter above the distributor. It's 1 meter above the distributor. Okay? And I have the technique of desoxygenation, reoxygenation. I put, for example, this compound to remove the oxygen. I have, for example, the saturated oxygen. When I put this compound with the cobalt as a catalyst, I can remove the oxygen. Remove. After that, we have reoxygenation. And by studying this part of reoxygenation, I can have an idea about the rate of mass transfer. Is it rapid or lower? Okay, by analyzing this curve. Okay. So I have this equation. You have an idea about Cayley, the coefficient of transfer. I have to measure this coefficient, indicating the rate of oxygenation or not. Okay. I use also SDS for this to reduce the coalescence, the presence of foam for propanol. Also for butanol, you can have the foam also. It's not good for us because it can reach a lot of volume. Okay. And when I have foam, the signal is not the same as you can before. You can to compare before. You have the signal is clear here. Without foam, it's clear. But with the foam, disturb the signal. Okay? Disturb the signal. Okay? We have the same desoxygenation, reoxygenation, but there is some fluctuations. Okay? And we can calculate the coefficient of transfer. Then you can have an idea about, and we have a comparison between water, ethanol, propanol, butanol. And the best one is water and ethanol. For mass transfer, the oxygen, the presence of oxygen is more for water than for butanol. When we put surfactant, we decrease the transfer of oxygen. Okay. So with increasing carbon number, the interfacial area increases, proven by gas retention results. This proves that the decrease of in this coefficient is greater than the increase of interfacial area. And I finished this part. This part is very hard. But if I can give you some idea about this part, because we analyze the signal. We can analyze the signal to have an idea about the statistic and the presence of gas, what is the regime transition, and so on. I can give you some picture, some figures, but I stop this presentation. Okay. So the bubble column for us is to measure the mass transfer of gas. I give an example of oxygen, but I can have the other type of gas to have an idea about the rate of the mass transfer to remove the gas from gas to liquid. That is the idea. Okay. So I finished this presentation. There is some question. It's the chemical engineer aspect or environmental aspect. According to the periodicity, I have a periodicity here. Frequency or periodicity. Okay. Because I analyze the signal from pressure flow. I can analyze the influence of gas in the signal, because the signal is increased by the presence of gas. I have a lot of gas. It's not the same as a little gas. In the signal I have to analyze the signal. What is the significance of the signal? High frequency analyzes periodicity. Maybe there is periodicity in the signal. Maybe. That's why I use some okay. I give some picture. Okay. This is a periodicity. In my signal, for example, when I use water, ethanol, propanol, butanol, there is difference. I have some peak indicating frequency. The inverse of frequency is periodicity. There is periodicity in the signal. Indicating the presence of ethanol, I can distinguish between ethanol, butanol, propanol, water by the peak, by the frequency, because the butanol behaves different than propanol or than butanol according to the signal. You see, you have a difference between other. By analyzing, you have some frequency. The frequency is, for example, 5 hertz. 5 hertz. The inverse of 5 hertz, you have an idea about the periodicity, okay? Okay. Yes, we talk about the coherence. For example, to have an idea about the transition between homogeneous, between bubbles, same bubble, same size bubble, and heterogeneous signal, we can use this. For example, here we have, when I reach 1, there is coherence. When I reach 1, after, for example, after 2, 3 centimeters per second, I have an idea about the difference. There is a difference. Here. There is a difference. Okay? Okay. This is a periodicity. This non-periodicity here, for example, butanol, for propanol, but for water, there is periodicity. It's not the same. You see, it's not the same. After a certain gas, for butanol, propanol, and water, I can distinguish between water and presence of liquid by regarding the signal. If I have this signal, I'm sure this is a coalescent system. If I see this non-coalescent system, because no periodicity in non-coalescent system. For coalescent system, there is periodicity. Okay, there is periodicity. Okay, that's all.
Check. Okay, for the online participants, maybe if you have any questions, you can raise your hand and open your mic.
Have you one publication? One international, one national publication. Have you an idea about how to publish an article? Yes. We do this experiment, publication. What kind of journal you use, for example? Your national journal or international journal or?
For the master program,
Yes, yes.
for the to finish our study, we should publish in both international journal, minimum one of
Minimum one.
international conference. I mean,
Conference.
yes,
Conference, yeah.
international conference plus one national conference or one national journal. But it should accredited by Sintatu in Indonesia. It's accredited journal.
Is it easy to publish?
It based on my experience and my friends, it's more like the QE of the
Q1 or
publication.
Q2? Yes, yeah, yeah, yeah.
Because there is so many submitted journals, so the process maybe took for more than 6 months, maybe for the first review.
Q2.
No, for the national journal.
National.
Yes. But some of my friends already joined the ICNS yesterday.
Yes.
That can be used for the publication. Itu kamera. Itu. Ya, nanti yang akan dapat ngomong kalau Pak Mario nanti keterangan Pak ini saya tapi orangnya aja info ya ini bukan itu ya tapi yang kedua memang sampaikannya untuk tempat nanti ya
Yes. Masih ada pertanyaan?
Just to have an idea about Morocco, this is the map of Morocco. It's in north of Africa. This is Morocco. The capital is Rabat, not Casablanca. Rabat. It's my city, Rabat, but I work in Casablanca. Okay. There is a Mediterranean Sea and the Atlantic Sea. You have two, Atlantic and Mediterranean Sea. This is some example. Different kind of climate and geography. We have mountains, we have forests, and we have Sahara desert also. A lot of in the same country we have mountains, forests, desert, etc. Some pictures. Now it's we have snow now, right now. Snow in mountain. We have snow in Morocco. Okay. This is Hassan's second mosque in Casablanca, among the greatest mosque in the world, maybe the second one or third one in the world. Okay. This is Casablanca, modern Casablanca. Okay. Okay. And another. There is also old city. Old city. Here, old city. Okay. That's all. Okay. This also. Yes. Oh. Superior technology.
Okay, ladies and gentlemen, thank you. Thank you for our lecturers, also for our moderator for such an enlightening session. And to express our gratitude, we would like to present you with a certificate of appreciation. Maybe Mr. Mariono can give the certificate to Professor Essadki.
Professor Abel, thank you so much for this nice lecture, and this is my certificate for you. Thank you.
Okay, once again, congratulations. Please give applause to the professor. Okay, thank you, Professor. And the second, we also have a certificate of appreciation for the moderators, Mr. Mariono, which is will be given by Ketua Himpunan MIL, Mas Arif Setiawan. Please. Oh yeah. Okay, my yes, we take the photo together for all the participants.
Gimana? Kita duduk sini. Sini lah. Tapi di sini. Bahas kamu berdiri di sini nggak apa-apa. Nggak apa-apa, Mbak. Biasa. Ini bisa saya. Oh ya. Please, sit here. Nggak apa-apa ini nggak apa-apa. Bahas berdiri ya Pak. Duduk di sini Pak. Nggak apa-apa, tak kasih sini. Yuk kita duduk. Sampai sini. Please, silakan. Nah, ya, gitu. Nah,
Please be careful.
Sebentar ya. Oh, iya. Jadi lah. Belum, satu kali lagi. Ya.